fundamentals of basic conservations of equations, all like non-viscid incompressible flow. Okay, where we are not going to cover any viscous flow, only incompressible and inviscid flow will be covered, right? So flow over the, so before going into the actual aerodynamics, we will just follow up with all the fundamentals. Okay, so before building and before you'll go for to make a building, we'll just think about a brick, right? Like that same thing we will do in this aerodynamic portion. So before that, we will just understand all the fundamental equations and fundamental behavior of those equations into the actual aerodynamics, right? So what we actually going to cover in the full aerodynamic syllabus. So first of all, we will discuss some fundamental principles and equations. Okay. And we are going to derive it, not just we will just give the formulation and use it. No, we are not going to do like this. Okay, what we will do, we will derive all the fundamental equations so that you will be very much habitual with all the fundamentals, right? That is more important. Okay, if we will give time in the fundamentals more, you can understand it more clearly. Okay, right? So that will be our purpose for this aerodynamic syllabus, right? So before starting this, we will just focus on fundamental. Now secondly, then we will discuss about the incompressible inviscid flow. Basically in aerodynamics, we are going to cover this part only. We are not going to touch any viscous flow or compressible flow. That will be discussed or covered in the different section, right? Then this is the basic, right? Then finally we have to move to our aircraft slowly. Then we will think about the airfoil. Okay, airfoil. Then we will discuss the behavior of the incompressible inviscid flow fluid over an airfoil, how it will react. Okay, so that we are going to cover in this first. After airfoil will be covered, then we will enter into the wing. Okay, finite wing theory. Okay, so how this behavior will go will be shown on the finite wing. Okay, then that will be the our syllabus for full, and finally we will discuss some type of different wings and how it will behave on the aircraft. Like that, it will be finalized. Okay, so what I will suggest you, if you are going through this, just we will just focus on whatever notes I will be giving PPT. So that notes and PPT will be very much sufficient. You don't need to go to any different types of books. See, if you will go to different types of book, different you can understand, you can go for your reference, but mostly full syllabus I will be covered in this PPT. Okay, so every derivation, everything would be there. With that numerical portion and assignments, you have to do it from IGC gate assignment and practice problems. For this reference, you can go to Fundamentals of Aerodynamics, JD Anderson. So in full of my career, I have used this book only. Okay, but some more reference for some particular topic I'll be giving with the all the whenever we will move ahead. Okay, for particular section only, I won't suggest you to fully you have to cover from different number of multiple book, right? Then all the previous year question paper you can just so this will be the just full that you have to cover for aerodynamics. So every question, each and every part will be covered here, and you would understand like, okay, I can do all the questions from like PPT and all whatever is given. The notes from there only you can easily solve all the numericals and all the basic fundamentals from the gate. Okay, then let's start with the aerodynamics, some fundamental principles and equations that these are basic principles we are going to cover. But you can understand this full, we will not be able to cover in this, but we will see how much we will be covering here. Review of vector relation. You can see from here, we will start with the vector relation. What is scalar, what is vector, and how what are the different relations for the vector, because before building any fundamental we have to understand the mathematics part also, right? So review of vector relations. Then we will think about, okay, you are entering into aerodynamics. So before that, you have to understand the fluid element. Okay, fluid element you are going to understand. And why the fluid element? Because you are going to apply all the basic fundamental principles on that fluid element. So that fluid element, I'll call this is a model. Okay, model of a fluid. So that model, you are going to choose it, and all the principles, all the fundamental equations you are going to apply on that, right? So you have to understand what is the control volume, what is the fluid element, what is the control surface, and what are the different types of model you can choose for understanding the proper understanding of the aerodynamics. Okay. Now, like basically, we will be covering all the integral form of the continuity, momentum, and energy equation with the full derivation. Because I understand this. This is a very important part that usually students miss. Okay, usually what they used to do, like skip all the part continuity, momentum. Okay, I understand this, but I think this should be done very deeply, and you should understand all the integral form, generalized form. Then you have to dictate it according to your situation: steady flow, unsteady flow, uniform flow, non-uniform flow. According to that, you can just go to the your requirement. Okay. Then application of these continuity equation, momentum equation, energy equation. Yes, energy equation would be very much useful for the gas dynamics, compressible flow. Okay, not for this viscous inviscid and incompressible flow. Okay. Then the application of momentum equation, right? So momentum equation, basically it will we will show you in the how to calculate the drag of a two-dimensional body by using the momentum equation. And based on this, one question already came into some gate 2011 or 12. Okay, so first of all, we will understand how to apply the momentum equation. Okay, then we will understand some questions. Then we'll go to then you can easily solve that numerical that is came into gate. Okay, then we will be covering substantial derivative, fundamental equations in terms of substantial derivative. So all these fundamentals I'm giving for starting the actual aerodynamics. Okay, so now path line, streamline, streak line, you all will be familiar with this, but we will revise it all. And then angular velocity, vorticity, strain, circulation, stream function, velocity potential function, relations between the two. So all these we will be covering as a fundamental, right? Like this is the basic thing you have to understand before going into actual aerodynamics. Okay. So let's just start with the scalar field. So as the name suggests, you know what is scalar? Anybody? Ah, yes. Anybody? What is the scalar? Scalar, vector. Do you know anything? Have you heard about scalar?
Yes, sir.
It's a
Those
quantity
quantities
is
which have magnitude only.
Yes, it does not have any direction, only magnitude, right? If you'll talk about the field, scalar field, what do you understand by scalar field? What do you
Field has
understand by field? Just let's say, let's check with the one by one. Scalar, you understood. What is field?
region, sir.
Region, definitely. That's what field means, right? So, a scalar quantity given as a function of coordinate space and time, that is called the scalar field. Can you give any example of scalar? Scalar quantity, let's say in aerodynamics or fluid mechanics, anything?
Mass,
Mass, yes.
Mass, pressure, current,
Pressure, current, pressure, temperature, density.
density.
Yes, all are scalar field, right?
Yeah.
Scalar. If this scalar will be the function of space and time, if this scalar quantity will be the function of space and time, what do you mean by space x, y, z, right? The coordinates. Okay, at different location, this value of the scalar quantity would be different. So that is called the function of the coordinate space, right? And the time. Okay, so let's say, for example, I'll see pressure, temperature, and density. Now you can see pressure, temperature, density. Pressure is the like function of x, y, z, and time. This is space. Okay, and this is time. If you will show this pressure scalar quantity is the function of space and time, that is called the scalar field. Okay, okay, there are different this is the Cartesian form, okay, cylindrical form, spherical form. uh, okay, in cylindrical form you are defining by r, theta, z. Okay, and in let's say this is the cylindrical form, but mostly this is a let's say spherical form. This is Cartesian coordinate. These are the coordinates like cylindrical coordinate, spherical coordinate, and this is the Cartesian coordinate. Okay, right? X, Y, Z, R, theta, Z. Mostly you deal with the Cartesian coordinate and the cylindrical coordinate only, not with the spherical coordinate. These are the coordinate system only. Okay, how you can define your coordinate system, how you can define the location of any particular pressure, particular point, how you are defining, that's what it signifies, right? So similarly, as a pressure we can define density, we can define temperature. Okay, if these are the function of space and time, right, that is called the scalar field. Similarly, we can define the vector field also. How can you define the vector field?
Vector in any vector which is a function which depends on a space and time.
Very good. Yes, that is the vector field. Any vector quantity that is the function of space and time. That's it. That is the vector field. Space and time. Yes. Okay. Any example of vector?
Acceleration.
Acceleration. Right. So before accelerating, you need velocity, right?
Yes, sir.
Yes, sir.
Yes. So velocity also. Any other vector quantity you want to add?
Displacement.
Force, sir.
Work done.
Work done. Okay. But is it okay? Vector quantity, it is fine. Is it will be work done if you will study in aerodynamics? It will be helpful.
So force and momentum.
Okay.
Torque, sir.
Sorry.
Torque.
Torque. Okay. Okay. So any vector quantity you can take, that will be the function of coordinate space and time, right? That will be the vector field. So let's take the example of velocity only. Velocity you can write in vector xyz component of the velocity vx, vy, vz, and vx, vy, vz will be the function of xyz space and time, right? So that will ensure the field. Okay, because it is giving the function of xyz and time, so it is actually giving the field. So we are defining vector, so it is the vector field. Okay, so generally you will study, suppose a vector field, this, suppose this vector field. So you should know what is vector field, right? So now you know what is vector field. You can understand it very clearly whenever it will come. Okay. Now, what is gradient of a scalar field? Now, scalar field you understood, right? Now you have to find out what is the gradient of scalar field. What do you understand by gradient word? Can anybody?
So
Gradient,
if
just
you
huh.
consider a space, if you
Yes.
consider any volume, then within that volume, the quantity keeps on changing. It will not be a constant. At the
Yes,
lower
yes.
part of the volume, it may be high, or at the upper part, it may be low. So whatever quantity we are considering, if that is varying within a certain volume, then we call it as a gradient.
Yes, gradient means itself change, rate of change or
Variation, sir.
change, right? So you have to show the change of a scalar field. You have to find out the gradient of a scalar field. Okay. So this gradient, the change can be in any direction, like any coordinate system you take x, y, z, right? So x, y, z coordinate system, right? So what you have to take, there is a del operator. Okay, del operator I del by del x. It is a vector quantity. Okay, plus unit vector j del by del y plus unit vector k del by del z. You know what is I, j, k?
The same unit vectors.
Yes, unit vector in x direction, unit vector in y direction, unit vector in z direction, right? So this del operator you are going to use for finding the gradient of a scalar field. Yes, you can see it clearly. This del operator is basically showing the gradient, like it is differentiating with the x, y, z. It is giving the rate, right? Rate of change with x, with y, with z. Okay. So like that, or with time also you can add that. I'll add it and I'll tell you separately what is local derivative, conventional derivative, total derivative. That will come further. Like, but at this moment, I want to dictate this del operator. That means it is giving the rate of change with something, with respect to something. Okay, with respect to space, with respect to time. So if you are finding the gradient of a scalar field, you have to take a scalar field P, okay, and apply the del operator. That is called the gradient. Okay. If any quantity, any P is given to you, right? Like P equals to 2x plus 3xy plus 4z square. Can you find this del P, gradient of pressure? This is a scalar field I have given. This is a scalar field of pressure field, I can say. Can you calculate this del? Del P means gradient of P. Yeah, based on this also question is already came into gate, or it can come. Can you calculate? Just apply this,
Yes, sir.
right? Just apply this and you can easily find out. So P is a scalar field, scalar quantity. Del is a vector quantity. What will be del P? Del P
Vector
is,
quantity.
Vector quantity.
yes, very good. It will be vector quantity. It will be having both magnitude and direction, right? Both the things it will be having. So what the magnitude will signify for the gradient, what the direction will signify for the gradient. Okay, the significance of gradient. Yes, the first point, the significance of its magnitude. Right? So significance of its magnitude. So its magnitude is the maximum rate of change of P per unit length of the coordinate space at the given point. I'll show you with the figure also. Okay. So the magnitude will actually tell the maximum rate of change of P per unit length at a particular location. Right? Okay. That's what the magnitude of gradient will show. What its direction will represent? Its direction. So definitely del P is a vector quantity. It will be having its own direction. Am I right?
Hello, sir.
Yes.
Are you changing any slide, sir?
Yes.
Sir, it's showing only one slide, sir. what is going to cover in aerodynamics syllabus?
No, it's not changing, huh?
It's changing,
No,
sir. I
it's
think it's
changing.
gone
yes,
from
sir,
its
it's
side.
changing.
Maybe for you, you can do one thing. You can just join it again, rejoin it.
Okay, sir.
If it's changing for all, maybe your network issue is there. You can rejoin. I'll wait for you. Okay. Who was that? So if he will join, we can start. Okay, maybe he will. You can see my slides, right? Everybody.
Yes, sir.
Okay. Right. So, just a second. Right. So this del P is a vector quantity. So it will be having magnitude and direction. Based on this, you can expect any type of question in GATE. Okay. Nothing is silly in the GATE. They can ask anything. Okay. So you have to be prepared with everything, whatever is basic, everything, and nothing is silly to ask in the class also. You are free to ask any type of silly question that won't be silly. Okay. That will even that is possible, like whatever you will ask that silly question that can come into GATE. That's it's like that fundamental things is going to come into GATE, right? So you have to be very much careful. Okay, I hope he had joined already. Okay, we'll talk about the direction. If you will try to find out the direction of del P, that direction will be giving the direction of maximum rate of change of P at that particular point. Okay, now you would understand by seeing this figure. Now, next slide, is it visible?
Yes, sir.
Okay. Right. You can see this figure, right? This figure is visible, right? Figure 1.
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Then it's changing to all. Okay. Then this just illustration of the gradient of a scalar field. How you can illustrate. Okay. This is a XY plot. You can see how in XY plot pressure is changing. Okay. This is P1 line. P1 line means pressure is constant along this line. Okay. That is the pressure constant line. Okay, iso lines for the pressure, you can see. So this is P1, that is constant along this line, along this curve. Then P2 equals to constant along this curve. P3 is constant along this curve, right? Now you will take a random point P. Okay, you know how pressure is varying related to x, y, z time. Okay, pressure would be the function of x, y, z, t, because it is a scalar field. It is a pressure field. So pressure field, it will be the function of x, y, z, and t, right? So definitely it is going to vary if you will change one location to another location. Let's say you are at point P here, xy, okay, and you want to calculate the magnitude of this del P, that is going to give you the rate of change of P per unit length at this particular point, okay, in the coordinate system. So what
Sorry
you are
to
going to
interrupt.
do?
So I
Sorry?
can't see the screen after rejoining.
Oh,
Yes,
after
sir.
rejoin also you cannot see the screen, no?
Yes, sir.
Yes, sir.
Okay. What can I do? Everybody can see, right?
Yes, sir.
Yes, sir.
Okay. Okay, I'll share it again. Maybe. So the pressure P1, this is the line that will give the pressure is constant, that is equals to P1. Okay, then another line, pressure is constant, that is P2. Another line, pressure P3. Okay, this is a pressure filled here, that is the function of x, y, z and t. Okay, this is the pressure filled in xy, not in even z, because you can see it's 2D, so that is not there, time may not be there. Okay, but let's say we are discussing only xy coordinate. Okay, because you can see it's a 2D pressure field only we have taken, right? So at any point, okay, any point P, this P indicates the pressure, then you can take it X point. X is also okay. Some other A point. Okay, some point A. At this point, you want to calculate the rate of change of maximum rate of change of pressure per unit length. Okay, the question can be in different way. You know the significance of gradient of pressure, right? The question can be in different way. Consider the scalar field is given like this: p equals to 2x plus 4xy plus something 6z square, something like that. Okay, the pressure would be given, pressure field is given in this way, and it is asked calculate the maximum rate of change of p. Okay, the calculate the maximum rate of change of p per unit length. They won't directly ask calculate del p. They will ask what is the maximum rate of change of p and what in what direction. Okay, they can ask in that way. So we have to look all the factors by which they can ask the question, right? Only then we can understand the problem exactly, right? So at point A, that is the function, let's say xy, at any coordinate xy we wants to calculate. So del p, the magnitude will give the maximum rate of change, and whatever its direction would be there, that direction of the maximum change in p at that particular point xy a. Okay, that direction you will give. So if you will assume that parallel to this direction, these dotted line drawn, these are the gradient lines. Okay, parallel to this tangent to these direction, you can draw the gradient lines. Okay, so these are the iso lines, as pressure here is constant on this line, pressure P2 is constant over this line, P3 is constant, so these can be called as like iso lines. Okay, then it is just mention like P3 is greater than P2 is greater than P1. Okay, you understood, right? Any doubt?
No, sir.
No, sir.
Right. Now we are now next topic is directional derivative. Okay, directional derivative. What do you understand by this name? Forget about you don't know anything about the directional derivative. What can you understand by this word itself? Directional derivative. Can you tell me anything about?
Finding a derivative of something in a particular direction.
Correct. Very good. That's what it means. Okay. Particular direction would be given to you and you have to find out the derivative of that. That is the directional derivative. Right. But the derivative can be in different way, like in x coordinate, y coordinate, z coordinate, time coordinate. Right. That can be. So let's say in any direction s is any direction. Okay. If you are finding the dp by ds in that direction, you are getting the differentiation derivative. Okay, you can find this derivative by using this del operator. Okay, right, del p dot n. This is the direction in which n is the direction in which you want to find out the derivative, right? So instead of solving this, what we will do, we'll just get the del p dot n, that in the direction, in that particular direction we will find out the directional derivative. Okay, in the above equation, dp by ds is called the directional derivative in the x direction. Note that the rate of change of p in any arbitrary direction is simply the component of del p in that direction. You understood this part, right? Directional derivative, we can just take any arbitrary direction as we can take. Okay, dp by ds. What you have to do, you have to find out this del p in that particular direction, whatever the whatever the direction you want the derivative, that this is the derivative, this will work like a derivative, and this by applying the direction you will get the directional derivative. Okay, right. So in Cartesian coordinate, del p, okay, now you can show it. You can just see this in Cartesian coordinate x, y, z. Okay, let's say in 2D, it's 2D only, x, y coordinate system. If you will take any del p in this particular direction, n, in the s direction, arbitrary direction s, direction you have to find out. In that particular direction, if you are going to calculate the directional derivative, del p dot n, okay, dp by ds, that is called the directional derivative. Based on this also questions came, but the same thing you will be studying in mathematics also, but you can cover it from here also. Okay, directional derivative, some question already came into GATE, but basically it covers into mathematics. Okay, and then what is the divergence? Divergence of a vector field. Earlier you have studied gradient of a scalar field, right? Gradient of a scalar field. Okay, now you are studying the divergence of a vector field. Now definitely you have to do the divergence for a vector field only. You cannot use scalar field, right? Well, like velocity. Okay, if you will use this, okay, let's say consider a vector field v xyz r theta z or r theta phi in Cartesian coordinate, in cylindrical coordinate, in spherical coordinate. You can use it. Then only in Cartesian coordinate we will see this v xyz, vxi, x component of the velocity, y component of the velocity, z component of the velocity, right? So you can find out del dot v. Okay, so if you are finding out del dot v, what is del? Del is vector quantity, right? Del is a vector quantity. What is v? V is also a vector quantity, right? So vector dot vector, what will be the result?
Scalar quantity.
Scalar.
Yes, yes, very good. So that will be a scalar quantity. So del, you know, del by del x, this del by del x, unit vector I, j, del by del y, plus k, del by del z. Okay. Now you can use vxi, vyj, plus vzk. Or there are different notation for this velocity component in different book. You can take uvw, that is popular, right? Uvw also you can use instead of vx, vy, vz. So everybody know, very familiar with the uvw only. Small u, small v, small w, that also you can use. Okay, so this is nothing but the del dot v. So the x component will go with x, and I dot I. What is I dot I?
1.
1. Yes. What is I dot j?
0.
0. Yes, very good. So dot product in the same direction, it would be 1. in perpendicular direction, because I, J and K are mutually perpendicular to each other, right? Am I right?
Yes,
I,
sir.
J, K are mutually perpendicular to each other. So whenever I dot I, it will be 1. I dot J, I dot K, anything perpendicular component, you will get the dot product, that will be 0. Why it is 0? It is I, J cos theta, right? Am I right?
Yes, sir.
If you will just
Sure.
solve it, the direction between the angle between the I and J, it will be 90 degree. Okay, cos 90 would be 0. That's why it is 0. Okay, similarly here I dot I means theta is 0,
0.
right? Theta 0 means cos 0 is 1, right? So that fundamental only is going to use here. So I, J, K, that will get 1, and here you will get a scalar quantity.
Sir,
Yes.
sir, can you share once again the screen, sir? I can't see, sir.
Okay, I'll share it. No problem. Yes, is it fine now?
Yes, sir. Thank you, sir.
Okay, no issue. Okay. Right. So this is the divergence of a vector field. Okay. Based on this also you can get the question. Okay. Similarly, whatever we have found out the significance of the gradient field, we have to find out the significance of a divergence of a vector field. Okay. What is this? Okay. Before that, we are going to cover some models of the fluid, because before entering into the like aerodynamics, we have to define some fundamental equations, right? But we have to apply these fundamental equations on what? We have to get, because it is not a solid body, right? For solid body you can find out, okay, this is the stress, this is the strain, and all you can find out, right? Because you can see that. But for fluid element, you have to assume, you have to understand, this is the model, and on which this we are going to apply all the fundamental equation, continuity, momentum, energy equation, all the equation we are going to apply on this particular model. So how this what are the different types of model are there for the fluid? Let's say for finite control approach, finite control volume approach. Okay, finite control volume approach. So what you can do, let's say flow is there, fluid is moving from left to right. Okay, you can assume a finite control volume fixed in space. So this control volume, this is a control volume, and it is enclosed by a surface that is called the control surface. Okay, some volume is enclosed by a surface, control surface. This volume is called the control volume. Okay, so this control volume, this finite control volume, we are fixing in space, and the fluid is flowing over the volume. So can I say, like, at every time the fluid will be different in this control volume? Can I say
Yes,
like this?
sir.
Yes.
Yes, sir.
Yes. Yes. If I will take another case, let's say this control volume itself is moving with the fluid. Okay, this is the first case. I'm taking this model in the fixed in the space, right? Fixed in the space, and I'm telling the fluid is flowing over this control volume, and I am just observing all the information: pressure, temperature, density, uh, viscosity, whatever I need. I'm just observing all the information, all the physical properties, velocity, acceleration, how it is changing with respect to space and time, how it is changing. It is uniform flow, non-uniform flow, steady flow, unsteady flow, compressible, incompressible. So you can just understanding your understanding from here, right? This is the fixed in the space. So every time fluid element would be different. Another case is you are assuming a control volume that is enclosed by a control surface that is moving with the fluid. Okay. But now I can say every time the fluid in this control volume would be same. It is not going to change. Can I say like this?
Yes, sir.
Yes. The properties is going to change definitely because it is moving due to moving effect. The properties, whatever you are looking for, that is going to change and that you can observe it. Okay. But this control volume is moving and all the time fluid element is same, right? This is the finite control volume moving with the fluid such that the same fluid particles are always in the same control volume. Okay, you understood this type of model, right? This is a finite control volume approach. If you are assuming a control volume, you can do by two way. You can fix it at a particular location, or it can be moved with the fluid. You can make it move like velocity is constant for it is moving with the fluid, whatever the velocity for the fluid element, fluid particles. Next is infinitesimal fluid element approach, a small fluid element approach. You are taking a small element of volume dV, right? And it is also having the same case. It is fixed at this point. Okay, every time the fluid element would be different at this location, fixed in space. Okay, it is okay, it is not moving with the fluid. And second case is it is moving with the fluid. Now you are observing all the information. Okay, this is the second approach. Okay, now what is the physical meaning of divergence of velocity? Okay, we have understood the physical meaning of gradient of a scalar field. Now we will understand the divergence of a velocity. Velocity means definitely it is a vector quantity, right? So divergence of a velocity, the physical meaning. Based on this, also one time question already came into game. Okay, what is the physical significance of velocity? Okay, what is the statement? And I'll prove it. Okay, don't worry, I'm just giving the statement now, and after this slide I will prove it. Or this is the this is the meaning of, this is the divergence of velocity. So del dot v, this symbol signifies the, tells the divergence of velocity. Okay, del dot v is physically the time rate of change of volume of a moving fluid element of fixed mass. You just listen it very carefully. Del dot v is physically the time rate of change of volume. Time rate of change of volume. Del v, let's say. Okay. Time rate of change of volume per unit volume of fixed mass. This is very important. Of fixed mass. Mass is not going to change. Okay. Fixed mass per unit volume of that element. So can you suggest, like, we are talking about the control volume, right? We are talking about the volume here. So if we are going to prove it, we have seen two models, control volume approach, and second one is infinitesimal small element approach. So which model will you suggest for this? If I'm going to solve this divergence of velocity, which model will you suggest for this?
Infinitesimal.
Infinitesimal. Okay, anybody else? Here you can see we are talking about the for a fixed mass, we are talking about the volume, right? Infinitesimal volume, if you will see, that is just a point. Okay, you cannot cover, you cannot show your volume. Am I right?
Yes, sir.
So I can take the model that will be control volume approach. Control volume approach, right? And this is also having two cases, like fixed in space or moving with the space. Fixed in space means every time the fluid element will be different, okay, and mass of the fluid element would be different. Can I say like this? If every time fluid element is different, mass of the fluid element in the control volume would be different
Yes,
for the
sir.
first case. But for the second case, if I will look, like it is moving with the fluid, and whatever the fluid element at time t, okay, the same fluid element, same mass of the fluid element would be there after time delta t, right? So is it just getting the same thing that I want from here, like fixed mass we are applying? We want fixed mass. So can we take this second approach? Second model can we consider for this particular case? Right?
No, sir.
No. Why?
Because elements are changing, their mass is changing.
Mass is changing.
No. Mass is not changing there.
Mass is not changing. For the first case, it is changing, definitely.
Yeah.
Okay. But for the second case, mass is not changing. At time t, the same fluid element was there. At time t plus delta t, same fluid element was there. Okay. So this approach, can I select?
Yes, sir.
Yes. Very good. So this is the point I'm telling why I will select this case, this model only. Okay. While proving it, I will select this model. So del dot V. But physically, if you will see, is it feasible to go with the fluid element? Is it like feasible to go with the fluid element, or is it feasible like we will fix our location at some point and we will see all the information? Are you getting my question?
Sir, can you repeat?
My question is it feasible to go with the fluid element and we'll check everything with the fluid element?
No, sir.
No. So what we will select for this case, this particular case, as this is just like for any model we can select, right? Because this is a purely theoretical portion. Okay. But if you will go for the practical cases, we have to select first case, right? Control volume, fixed in space. Am I right?
Yes, sir.
For this particular case, as it is mentioned, the mass will be fixed. Okay, for our convenience, we are taking the second model. That is also not wrong. We can take, because it is purely theoretical portion, right? So all the model, whatever you take, you just apply all the information and apply with all the limitations, apply all the fundamentals. You can select any of the models, right? So this is the physical significance. I'll show you one question based on this, that is, and I'll ask you something for this. So del dot V is the, you will tell this is the, what is this called? Del dot V. What is this called? This is the divergence of velocity, right?
Yes, sir.
Divergence of velocity. So this divergence of velocity would be equals to rate of change of volume d del V let's say small element we are changing, d del v by dt per unit volume for a fixed mass, that you have to take care. This is very important word, fixed mass. You're talking about the fixed mass. Okay, right? And what is the, like, how you are going to prove it? Just see it. We are assuming a control volume, okay, of volume V, and with the control surface S is moving with the fluid element with velocity V. Okay, so this is a small elemental surface ds I have taken. Okay, and after time delta t, this small fluid element, small surface, let's say ds, it will be reaching here after time delta t. So how much distance it has been covered? V into delta t. Can I tell like this?
Yes, sir.
Okay, right. So the direction of normal direction of this surface, unit surface, is n. You will see the significance of this direction also. So we are assuming the moving control volume used for the physical interpretation of the divergence of velocity. Now you want to find out the volume swept during this travel. Okay, this is the volume swept, delta v dt dot n in n direction. Okay, this is the distance covered into ds. This is the nothing but the that surface. Okay, area. That area you will just this area in n direction you'll add, it will become d capital S. Okay, so v delta t dot ds, this you call as equation number 1. The total change in the volume, if you want to find out total change, this is a small surface, right? If you will find out the total change, that means you have to integrate, right? And that integration would be surface integral, because over the surface only you are calculating this, right? So this is the surface integral, closed surface integral. Okay, I'll show this. Later on I will discuss about the line integral, surface integral, and volume integral also, right? But at this moment, just for a sake of convenience, just hold this. What is this surface integral? Surface integral v delta t dot ds. So that is called the second equation. Okay, if this integral is divided by t, the result is physically the time rate of change of control volume denoted by dv by dt. Okay, right. I can just do one thing. I'll just divide by time, dv by dt, 1 by delta t. So delta t will get cancelled out, and it is the rate of change of volume, time rate of change of volume. Instead of rate of change of volume, you can call it time rate of change of volume, and that would be equals to this v dot ds and surface integral. So, okay, at this moment I'm using this, but I will tell you after 2-3 slides what is the divergence theorem. So it is actually relating the divergence theorem, Stokes theorem, or gradient theorem. All these three theorems will actually relates the single integral, double integral, and volume integral. Okay, this is actually relating the double integral to triple integral. Just take the triple integration over a volume, and this will become del dot v, okay, and dv. Okay, so just I'm applying this divergence theorem here, and this double derivative is converted into triple derivative, triple integral. Double integral is converted into triple integral. Now what you can assume, just let us assume, let us just imagine that the moving control volume in the figure 3 is shrunk to a very small volume delta V. Okay, we'll just assume it will shrunk to a very small delta V. Okay, then at that time you'll just use this equation. Instead of V, you just use this del V dV, volume integral over del V instead of V, then del dot V dV. Okay, now if you will get the rate of change of delta V here, and if you will find out let's say integral over here delta dot V into dV. dV, if you will integrate over a delta V, this dV basically it will become delta V. Okay, like that you can write it. Can you do it? It is very small, right? If you will integrate over this dV, it will be basically this is only coming delta V. Okay, just del dot V is equals to time rate of change of volume per unit volume. Time rate of change of volume per unit volume. So we have proved it here, like the divergence of velocity would be equals to rate of change of volume per unit volume for a fixed mass. That you have to remember, for a fixed mass. Okay, so that is giving the del dot V. Okay, there is one question that came into gate, like consider a compressible flow. This is the question that came into gate, and one more question I'll ask related to this only. Consider a compressible flow where an elemental volume of fluid delta V moving with velocity V. Which one of the following expression is true? So this is the expression del dot V equals to 1 by del V d delta V by dt, del dot del cross V, rate of change of volume per unit volume, again del dot this. Okay, right hand side is same. Okay, so what is the correct option? Can you hear me?
Yes.
What is the correct option?
Option A.
Option A. Yes.
First one.
Yes, very good. So that is the question that is asked into gate. Based on this, the physical significance of the divergence of velocity, you can expect question related to gradient of a scalar field. Okay, so this is what the question is asked. Now my question is, now here consider a, okay, one more I will add. None of these. Okay. I will add one more, del dot V equals to 0. So these options I have added, two options. Now I'm not changing anything. I'm just making it incompressible flow instead of compressible flow. Now can you give me the answer? Anybody? Okay, first of all, let me know what is the difference between the incompressible and compressible flow.
Sir, F is correct option.
F is correct option.
What is that?
Sorry?
Nothing, sir.
F is the correct option. Okay, anybody else? Okay, first let me know about the difference between the incompressible flow and compressible flow.
Sir, in incompressible flow, density will remain constant till Mach number 0.3, and in compressible flow, density will change.
Means d rho will be 0 for incompressible flow.
Yes, sir.
Okay, that is density is constant. Okay, so do you know at what extent we can just like assume density is okay till this margin we can say okay it is compressible, incompressible. Do you know that margin?
So Mach number 0.3.
Mach number 0.3, correct. In case of density, like it is just instead of 0, it is something d rho is less than 5%,
Yes, sir.
right? So density, change of density should be less than 5%. Then only you are assuming, okay, that is the case we are assuming for the incompressible flow. Okay. Now, okay. Now, can you tell me why F is the correct option? Yes, please. You have given me the, what's your name?
So Anu.
Anu. Okay. Tell me why F is the correct option?
Sir, in momentum equation,
Mhm.
if we put rho is equals to a constant, then we will get this equation del dot v equals to 0.
Okay. Okay, let's forget about the momentum equation. I haven't teach you anything about the momentum equation. Whatever I taught you from here, this is the rate of change of volume, rate of change of volume per unit volume.
Yes, sir. From here, uh, for incompressible dense.
For a fixed mass.
Yes, sir.
Hmm.
So,
Now
if
tell me.
density is constant,
Mhm.
then volume is also going to be constant.
Yes. If density is constant, density is nothing but mass per unit volume. Okay. Mass is already constant. That is already in the statement of divergence of velocity, right? So mass is constant. Excuse me. Then if density is constant, definitely volume is constant. That is not going to change. Then the rate of change of volume is going to be 0. Am I right?
Yes, sir.
Yes. So del dot V would be 0 for incompressible flow. Whenever, if any velocity vector field is given, can you prove it? It is incompressible or compressible?
Which thing, sir?
If any vector field is given, let's say Vxi plus Vyj plus Vzk, then Vx is given 2x plus 3y, Vy is given 3x square plus 2z, and Vz is given 3z square plus 2xy. Okay, this is a velocity vector field. Now it is asked in the question, like, tell me this is a incompressible flow or compressible flow. Can you prove it?
Uh, to find that, we can find del dot v.
Correct. Very good. So you have to make sure del dot V is equals to 0 for incompressible flow. Am I right? Yes.
Yes, sir.
So this is a direct relation. You can find out easily. Find out this is okay. This flow is this is giving the incompressible. This is incompressible flow, and this is compressible flow. Based on this, also some questions came into gate, right? This question actually directly came. Del dot V is equals to 0. What is the condition for the incompressibility? Okay, directly this question came into gate. Or instead of this can be asked like velocity field is this, velocity vector field is this, and give me the del dot v. Prove it. Is it a compressible flow or incompressible flow? Okay. Directly, what you have to do? You have to find out the divergence of velocity. That's it. Right? Okay.
Yes, sir.
Right. And this question again can be manipulated in that way, like some volume would be given to you, okay, and they will ask what will be the rate of change of volume, okay. Can you calculate now? Let's say some volume is given to you, instead of this delta v, some value will be given to you, okay. They will ask directly, nothing is discussed, incompressible, okay. They will tell this, consider this compressible flow, okay, because compressible flow means volume is going to change, right? Mass is constant,
Yes, sir.
okay. So this can be manipulated, this question can be manipulated like delta v will be given to you, and they want what will be the rate of change of volume, and velocity field will be given to you. So first of all, you have to find out this. You multiply with the given volume, you will find out the rate of change of volume. Consider this is the compressible flow of having this velocity vector field is like this, okay. And we are considering this delta v or control volume is this much, and calculate, because it is a compressible flow, calculate the rate of change of volume, time rate of change of volume. Can you calculate?
Yes, sir.
Yes. Based on this also you can expect the question. So you have to twist your whatever the fundamental you are having, that only you have to twist, and you can easily get all the questions, you can easily do it, okay. Right. Now we will discuss curl of a vector field, okay. So curl, with the curl itself, like if you will do the cross product, consider a vector field of this. If you will apply cross product with del operator, del cross v, so this is directly you are telling this is the curl of v, curl of a vector field. Vector field is velocity, okay. So you can just write this del cross v in this way: I j k del by del x, del by del y, del by del z, okay. X component of this is the unit vector I, unit vector j, unit vector k, x component of del, y component of del, z component of del, then you put x component of velocity, y component of velocity, z component of velocity. I hope you are very much aware about this relation, but still I'll just give some time here. You can just block this, and del vz del y minus del vy by del z. Similarly, you can do it for the j, okay, j. But for the middle part, you have to see minus j, it would be there if you will directly you are doing, but reverse it is written j del of vx, okay. If you are just closing this, minus j, okay, del vz is here, del vz by del x, del vx by del z. Minus sign you have to use, but instead of that it is used in reverse. Now same thing you can do it with this, okay. Del by del vy divided by del x, like that you can do with the x component with y, okay. This is the basic funda to get the curl of a velocity field, okay. If any velocity vector field is given, you can very easily calculate what will be the like product of this. This is a vector, This is also a vector. What will be the result?
Vector, sir.
Vector quantity.
Yes, vector quantity. Very good. That will also be a vector quantity. Okay. But if you will see del dot v, okay, this is a vector. This is a vector. This divergence. What will be this? What will be the result?
Scalar.
Scalar. Very good. Okay. This will be the scalar. But cross product, if you will see, this will be the vector. Why it is so? Okay. I'll ask I cross I. We have
0.
0. Very good. I cross J.
K vector.
Yes.
K vector. Correct. Very good. J cross I or J cross K.
I
So,
vector.
so that how it is coming? It depends on the sine theta, right?
Yes, sir.
Okay. Theta, it depends on like 90 degree or 0 degree. How it is 0, how it is I cross J, it is 90 degree. Then you can take it, okay, in that way. Okay, right. Right. We will discuss a little bit about line integral. I know you are very much aware about the integral terms.
Guys, you are enjoying because we are past
Yes, sir.
40 minutes. Okay, then sir, continue.
Okay, okay, okay. We'll just little bit touch about the line integral. Line integral is okay. We will just consider a x y z, a r theta z, any vector quantity. That is, just assume a curve AB. Okay, just assume a curve C A to B, and assume a small elemental length ds for this vector A. Okay, how you are this is an open integral. Okay, if you will close this curve, that will become the closed curve. Excuse me, just okay. So just see the representation of this. Let ds be an elemental length of the curve. You can see here ds will be the elemental length. So we have to integrate over this a to b. Okay, for the curve C, we have to integrate from a to b, and just we are assuming this small elemental length ds. Okay, small elemental length of the curve, and n be a unit vector tangent to the curve. So with this tangent, we have taken one unit vector. Okay. Then define the vector ds is n ds. So it is giving the direction of this unit length. Okay. N ds. So the line integral of A along curve C from point A to B. How can you write? Like this, A to B. So this is a open integral. So you can use this inverted U. That is the open integral. A dot ds. Okay, that is the representation of uh, uh, like line integral. The same line integral you can use it for the closed curve also. Okay, for that just you have to use this closed curve instead of that open curve. You have to use this closed curve. Now you don't have to use this limit, right? So a dot ds. Okay. Similarly, we can just define the surface integral. So let's say for this surface is this curve is enclosing, this curve C is actually enclosing a surface. Okay, it is enclosing a surface S. Okay, so for this I want to integrate For this integration, first of all, we have to assume a small elemental surface. Am I right? Just assume a small elemental surface with unit,
Yes, sir.
with unit direction n at point P. Okay, elemental surface is ds. So this is nothing but okay. The three-dimensional surface area S is bounded by a closed curve C. Okay. Now you can just apply the surface integral. Define a vector element area as ds would be n into ds. So at that time we were using ds equals to n ds. That was for the line integral only. Okay, now it is a surface integral. So this S is defining the area, not the length. Earlier it was the length. Okay, small elemental length. Now it is a small elemental area. Just you have to don't get confused with this. Okay, ds equals to nds. In terms of ds, the surface integral over the surface S can be defined in three ways. Yes. It is, let's say, for the scalar, surface integral for a scalar P over the open surface S. Okay, over the open surface S, you can define this in this way. Okay, then a vector A over the open surface S, A dot ds. Can you tell me P ds? Can you tell me what will be the result for this? Is it vector or scalar? P ds. If you will integrate over a over this open surface S, what will be the result? P ds. P is a scalar quantity, ds is a vector quantity.
Vector.
Yes, very good. This will be a vector. What will be for this? This is a vector quantity. This is also a vector quantity. So this will be a
Scalar.
very good. Scalar. Okay.
Vector.
Then, yes, cross product will always be a vector. And cross product, you can do it with the vector and vector only. You cannot do the scalar and vector. Just remember, right? You know it very well.
Yes, sir.
Okay. Okay. If
Sir,
yes.
till which time we are going to over this class?
Just hold on. Just 2-3 slides is there.
Okay, sir.
Okay. So if the surface S is closed, you can use the closed integral. If it is open, you can use the open integral. And volume integral. So as this is the control volume, right? Enclosed by a closed surface. Okay, you can take small elemental surface and show the direction n. Okay, these are just a notation for the volume integral a dv, volume integral for a vector a over the volume b. Okay, similarly, okay, for okay, scalar and vector. So you can take it density. I have shown only vector only. You can take it density rho. Okay, right? So here you can take a vector, right? So the relation between the Stokes theorem, it gives the relation between the line integral to area integral. Okay, surface integral. This is a vector quantity. This is also a vector quantity. So del cross A dot ds. You can convert it into line integral. You can convert it into surface integral. Divergence surface integral. You can convert it into volume integral. Then gradient theorem. It will give surface integral to volume integral. Okay. So okay. So basic equations of the aerodynamics. Yes, these were the basic thing that I just wanted to touch. Okay, I don't want to enter into too much detail. Okay, because you know it very well. Then basic equations are mass is conserved. Okay, mass can neither be created nor destroyed. Then Newton's law that force mass into acceleration, momentum equation. Then energy conservation. the third basic fundamental equation is. So it can be only changed in one form to the another form. It cannot be uh, created or destroyed. Okay. Okay. So there are steps to build the basic fundamental equations, basic equations of aerodynamics. So these are the equations.
Sir,
Yes.
sir, have you changed the slide?
Yes.
But it's showing relation between line surface and volume integrals.
Oh, is it? Okay, I'll share it again. Just hold on.
No, for me it's changing.
For me, yeah. For me also it's changing.
Okay, no problem. I'll share it again. Can you see it now?
Yes, sir. Thank you, sir.
Okay, no issue. Okay. So these are the conservations of basic elemental equations. So how you are going to build your basic equations? Okay, determine a suitable model for the fluid of the fluid. You know it. What I mean, determining a suitable model. I have shown you 4 models, right? So according to your problem, first of all, set your model. Like this is the model, okay, and I'm going to apply all the basic fundamental equations on this model, okay. That is the first step you have to do. Then apply the fundamental physical principle listed in item 1 to the model of the fluid determined in item 2 in order to obtain mathematical equations which properly describe the physics of the flow, right? So before starting any problem, first of all, we have to define a suitable model, right? That is the first thing. Okay, that's what I had to share for today lecture. Any doubt, any comment here is
No, sir, everything is clear.
everything is clear. Okay. So my motive is basically to develop the basic first, because gate is nothing but it is not a complex thing. It is just basic thing. If you will understand your fundamentals very clearly, you can crack gate. Gate is not a huge thing, you know. Okay. Anything else? Anybody else wants to share anything or any doubt anybody is having?
Okay. This is like webinar tool, but since it's a demo class, you have to join without signing in. So we keep it on WebEx, but otherwise our tool is much. You guys will really like IGC online platform once class starts. Yeah. Any other concern or any other thing?
No, sir.
Mallikarjun, Haripriya, Jayaprakash, Mavya, Rohit, Sandeep, Sanjay, Sumit, Tejas, Varuni. All right. So fine then. I think we are already chasing 3 hours. Now you guys might be tired. So for any concern, you guys can contact me, and enrollment is open only till Feb 10th. If you are interested, try to join before because we have to finalize our mathematics batch before going further any admission. All right. Okay, then take care, guys. Thank you, Naveen sir, for
Okay, Sam. Thank
spending
you, Dinesh.
Thank you,
this
sir.
much time and guiding.